calculation where I use thermodynamic data to predict a delta S for a reaction. And you can find thermodynamic tables that give you standard entropies. And I'm going to write those down here. I'm just looking them up. In any chemistry textbook will have them. And then we'll talk about what they mean. So for ammonia, it's 197.2. And the units for these are joules per mole Kelvin. For oxygen, it's 205.0 joules per mole Kelvin. Notice that oxygen is a standard state element, oxygen gas, and yet it has a non-zero value for standard entropy. And that's because of the third law of thermodynamics. There is an actual 0 point for entropy. It's theoretical. It's at 0 K. But you can imagine building up from there, having oxygen, for example, at 0 K and then heating it up, and you would be increasing the entropy. And you would be increasing the entropy at a calculatable rate. And so that you should be able to get a finite, definite value for the entropy at, for example, 25 degrees Celsius, which is the temperature at which these values are reported. That's different from delta H values. So delta H of formation, or enthalpies of formation, we take our standard state elements as our starting point for forming everything else, and we have just made that sort of arbitrary decision to use those as a starting point. And since these are all changes in enthalpy, to go from a standard state element to another standard state element, the change in enthalpy would be 0. So that's kind of the difference between using thermodynamic data for delta H and thermodynamic data for delta S, is that for the standards that are reported are actual entropy values, not change in entropy values. Okay, for NO, 210.6. And for gaseous water, and you have to be careful because liquid water has a different value, 188.7 joules per mole Kelvin. Okay? So those are our values that we have to work with. So what do we do with them? Well, it's much like Hess's law. We're going to add up the entropies of the products, and we're going to subtract the entropies of the reactants. And that will give us a delta S, even though these are all S's. That will give us a delta S because we're subtracting reactants from products, and we'll get a change from that calculation. And the way that I like to think of it is that the products represent the entropy that we're creating, and the reactants represent the entropy that's going away. So that's why we're subtracting the reactants. Okay, we're going to multiply by all of the coefficients, because the more molecules we have, the more entropy we have. So this is an extensive property, just like delta H is. 4 times 2, I'm going to leave out the units for brevity here. You have them up above. Plus 6 times 188.7 minus 4 times 197.2 plus 5 times 205.0. Now I could have left out the brackets and just said minus 4 times 197.2 and minus 5 times 205.0. That comes out to be the same thing algebraically. All right, so if I add these all up, it comes out to be positive 178.8 joules per mole Kelvin. Okay, and I put the positive there to kind of emphasize the signs. Signs are so important in thermodynamics. Does it make sense that we have a positive change in entropy? Well, if you think about it, we're going from 4 moles plus 5 moles of gas, these are all gaseous state molecules, to 4 moles plus 6 moles of gas. So we're increasing the number of moles of gas by 1 mole. And whenever you increase the number of moles of gas in a reaction, most times you get an increase in entropy unless it's countered by something else, but the great majority of cases you will get an increase in entropy. Okay, so that positive value makes sense, and in fact the reverse reaction would be a negative 178.8. Okay, so so how we interpret this 178.8 is that is the value that the change in entropy would have if we put 4 moles of ammonia with 5 moles of oxygen and got 4 moles of NO and 6 moles of water as products. What if we wanted to know what is the change in entropy if we just added 1 mole of ammonia, for example? So what if we wanted to calculate the change in entropy for 1 mole? And for lack of a better way of notation, for 1 mole of per mole of NH3, I'm just going to write it like that, okay? And all you have to do is do a little bit of dimensional analysis. So I'm going to take my 178.8 joules per mole Kelvin, and I am going to do some dimensional analysis. I'm going to try to get rid of, and oh, let me just add something here. This is moles of reaction. So remember, moles of reaction means the molar interpretation of the reaction as written. So as I said before, what that means is for 4 moles of ammonia, for example, okay? What if we wanted to know it per mole of NH3 instead, okay? We're going to do some dimensional analysis. So we're going to put moles of reaction on top and moles of NH3 on the bottom. And for every 1 mole of reaction, there are 4 moles of NH3 reacting, okay? Because by definition, this whole thing, all these coefficients up here are one reaction. So that's one single unit there. That one single unit has 4 moles of NH3 in it. And so writing it this way, you can kind of see how the units work out. The moles of reaction cross out and give you moles of NH3. And this value happens to be 44.7 joules per mole NH3 now, times Kelvin. And so now you can, if you were to use this process and scale it up or down, you know the joules for every mole of ammonia, and you could just multiply that by however many moles of ammonia you have to know what the change in entropy is going to be for any scale of this reaction.